Seismic conceptual design of buildings. Again, the reference book for this discussion is the book by Hugo entitled Seismic Conceptual Design of Buildings, Basic Principles for Engineers, Architects, Building Owners, and Authorities. So basic principle number 8 states that discontinuities in stiffness and resistance cause problems. Modifications in the cross-section of bracing systems over the height of a building cause discontinuities and lead to sudden variations in the stiffness and resistance of the building. So this can cause irregularities in the dynamic behavior and disturb the local flow of forces. An increase in the stiffness and resistance from the bottom up is generally less favorable than the opposite based on the previous illustration shown in the previous slide. In any case, the calculation of the sectional forces and the design of structures, as well as the detailing of the discontinuities, must be conducted very carefully. So we have here an illustration, the transition from a reinforced concrete structural wall to a frame structure causes large discontinuities in stiffness and resistance. So basic principle number 9 states that two slender reinforced concrete structural walls in each principal direction is highly recommended. Just like in the illustration here, one reinforced structural wall in this direction and the other on the other side. Reinforced concrete structural walls of rectangular cross-section constitute the most suitable bracing system against seismic actions for skeleton structures. The walls may be relatively short in the horizontal direction, for example 3 to 6 meters, or about 1/3 to 1/5 of the building height. They must, however, extend over the entire height of the building. In a zone of moderate seismicity, in most cases, two slender and capacity designed ductile walls in each major direction are sufficient. So the type of non-structural elements can also influence the selection of the dimension of the bracing system. So to minimize the effects of torsion, the wall should be placed symmetrically with respect to the center of mass and as close as possible to the edges of the building. Considering seismic forces transferred to the ground or the foundation, corner walls should preferably be avoided. When the walls have L cross-section or U cross-sections, the lack of symmetry can make detailing for ductility difficult. So reinforced concrete walls with rectangular cross-section can be made ductile with little effort, thus ensuring a high seismic safety. We have here such reinforced concrete structural walls take up only little space in plan and elevation. So the reinforcement of reinforced concrete structural walls is relatively simple, but it must be detailed and laid with great care. So the figure in here shows a capacity designed ductile wall of rectangular cross section which was added to an existing building. So we have here, this skeleton structure has reinforced concrete structural walls in the transverse direction at two building corners. So the structural walls were included as prominent elements in the architectural concept, just like this one. So basic principle number 10 says that we should avoid mixed systems with columns and structural masonry walls, just like this one. Columns and structural masonry walls. Mixed structural systems with concrete or steel columns and structural masonry walls behave very unfavorably during earthquakes. The columns, in combination with the slabs or beams, form frames, which have a substantially smaller horizontal stiffness than the masonry wall. So the earthquake actions are therefore carried to a large extent by the masonry wall. So in addition to the inertia forces from their own influence zone, the walls must resist those from the parts of the building with the columns. So this results in a seismic resistance considerably less than that of a pure masonry construction. So when masonry walls fail due to the seismic actions of the or deflections, they can no longer carry the gravity loads, which usually leads to a total collapse of the building. So mixed systems of columns and structural masonry walls must therefore be absolutely avoided. Furthermore, such mixed systems prove to be unfavorable because of their lack of flexibility with regards to increasingly frequent building modifications required by changes in their use. So removal of masonry walls require heavy structural interventions which are costly and can impair the building functionality. A consistent design of the structure as a skeleton structure, such as columns only, with some slender reinforced concrete structural walls extending the entire height of the building, is thus also in the long-term interest of the owner. So as the interior partitions are non-structural elements, they are easy to refit in case of changes in the building's use. So extensive structural modifications rather are therefore not necessary. So we have here in the illustration, this structural stairway wall will be destroyed by a relatively weak earthquake. A total collapse of the building may result. So basic principle number 11. Basic principle number 11 says that we should avoid bracing of frames with masonry infills. So it is still a common opinion that filling in frame structures with masonry walls improves the behavior under horizontal loads, including seismic actions. This is true only for small loads and as long as the masonry remains largely intact. The combination of two different and incompatible construction types performs poorly during earthquakes. The frame structure is relatively flexible and somewhat ductile, while unreinforced masonry is very stiff and fragile and may explode under the effect of only small deformations. At the beginning of an earthquake, the masonry carries most of the earthquake actions, but as the shaking intensifies, the masonry fails due to shear or sliding. So the appearance of diagonal cracks is characteristic of a seismic failure. Two basic cases can be identified. Either the columns are stronger than the masonry or vice versa. With stronger columns, the masonry is completely destroyed and falls out. With weaker columns, the masonry can damage and shear the columns, which often leads to collapse. So in here, the columns were clearly stronger than the masonry. So the masonry fell out while the frame remained standing. So in this case, the masonry was stronger. So the columns experienced significant damage and were partly sheared. Nevertheless, the frame is still just standing. So in here, the masonry was also stronger in this case. It sheared the relatively large columns, these parts. We also have here, these diagonal cracks are typical of reinforced concrete frame masonry infills. So basic principle number 12 says that we should brace masonry buildings with reinforced concrete structure walls. Just like this one. If we are going to incorporate masonry, we should add structural concrete wall. So traditionally in many countries, houses and smaller commercial buildings are often built with unreinforced masonry walls made of clay. limestone, or cement bricks. So masonry is a good construction material in terms of thermal insulation, storage, and vertical loads carrying capacity. For seismic actions, however, masonry structures are not well suited. On one hand, they are relatively stiff, so they usually have a high natural frequency within the plateau area of the design response spectrum and therefore experience large earthquake actions. On the other hand, unreinforced masonry walls are rather brittle and generally exhibit relatively little energy dissipation. So generally, it is not possible to obtain adequate seismic resistance and additional measures are therefore necessary. So a possible solution consists of bracing unreinforced masonry buildings with reinforced concrete structural walls. Hereby, it is possible to limit the horizontal deformations of the masonry and therefore preserve its gravity load carrying capacity. So the reinforced concrete structural walls must be designed to be sufficiently stiff, the horizontal wall length and the vertical reinforcement ratio being key parameters. So they must be able to carry the seismic actions to transmit them to the foundations while remaining elastic. The horizontal deflection of the reinforced concrete structure walls under the design earthquake must not exceed the displacement capacity of the stiffest masonry wall. So we also have here such and also lower new masonry structures without bracing reinforced concrete structural walls are extremely vulnerable to earthquake. So this new three-story residential building with unreinforced masonry structural walls is braced longitudinally by a reinforced concrete structural wall in each facade and transversely by an interior reinforced concrete structural wall. So this new four-story masonry structure is braced by one reinforced concrete structure wall in each major direction, just like this one and this one. There is also a long masonry wall in both directions that has a horizontal layer joint reinforcement and is anchored to the concrete wall. So structural masonry walls, reinforced concrete structural walls, and slabs should respond together when subjected to shear, compression, and if possible, tension. This is why it is recommended to fill in the joints between structural masonry walls and reinforced concrete structural walls with mortar. So basic principle number 13. Basic principle number 13 emphasizes that reinforce structural masonry walls to resist horizontal actions. So a possible alternative to basic principle number 12 for making masonry structures substantially more suitable for seismic actions is to reinforce some long masonry walls and thus stiffen them in the longitudinal directions. In this case, for example, vertical and horizontal minimum reinforcement and stronger vertical reinforcement in the boundary zones must be detailed. So thus, sliding in the horizontal layer joints can be prevented and a global ductility of 2 can be achieved. So the reinforced walls can therefore be considered as structural masonry walls for horizontal actions. So the horizontal displacement of the reinforced masonry walls for the design earthquake must not exceed the ultimate displacement capacity of the stiffest unreinforced masonry wall. So this is necessary to ensure that the vertical load bearing capacity of the unreinforced masonry walls is preserved. Right, so we have here an illustration. So reinforced masonry requires special bricks, particularly to incorporate and coat the vertical reinforcing bars. So worldwide developments in reinforcing systems and adequate bricks are underway. So these two pictures here show new developments in the clay masonry industry. So this type right here, this illustration, this type of vertical reinforcement is anchored, this one, is anchored at the top and bottom with U-shaped bars extending in two brick layers. So the bars used to anchor rather the walls to the slabs or lower walls are very important. So vertical pre-stressing can also improve the earthquake behavior of masonry walls by substantially increasing the vertical force. So in here, the strength and ductility of masonry walls in existing buildings can be improved with carbon fiber or steel plate reinforcements. So this is actually, or this actually falls under the modifications of the design so that we can add earthquake resistance to our building. So the plates must be glued on carefully and anchored in slabs. So it is also necessary to consider the capacity requirement perpendicular to the wall. So this applies in particular to gable walls or cantilever walls, to other masonry walls that are poorly restrained against horizontal forces, and for stronger earthquakes, also to walls supporting slabs. So here, the walls in the upper floors, which carried only a small vertical load, failed out of plane. So reinforcement, vertical pre-stressing, or glued-on plates can also prevent such failure. So basic principle number 14 states that or advises us to match structural and non-structural elements. So if deformation sensitive non-structural partition walls and facade elements are incorporated into a horizontally soft structure or such as frame structure, no, wala siya walls, no, columns lang and then beams. Without using joints, substantially damage may develop even for relatively weak earthquakes. So experience shows that in such cases, a building must sometimes be demolished. So even though the structure suffered no substantial damage. So a modern earthquake resistant design must therefore match the stiffness of the structure and the deformation capacity of the non-structural partition walls and facade elements. So the inter-story drift ratio and the vulnerability of the non-structural elements are crucial. So the skillful selection and combination of structural and non-structural elements can prevent damages even for relatively strong earthquakes. So that's why way back or boiling down back to our basic principle number 1, the architect and the engineer must collaborate in the outset so that selection of both the structural and non-structural elements can be decided at the early stage of the design. So here, the non-structural partition walls were destroyed, although the frame structure deformed only little and is hardly damaged. Even the windows remained contact. So the tendency is um, the frame structure is stronger than the non-structural partition wall. So in the case of earthquake, there is a high possibility that only the non-structural partition walls will collapse or fail. So in here, a collapsed partition wall is simply rebuilt until the next earthquakes, and not unless they do modifications of the design or not unless they match these non-structural elements with the structural elements. This partition wall will always fail during an event of an earthquake. So the glass facade of this new multi-story building survived a strong earthquake almost without loss, so owing to special flexible fastenings of the facade elements. So basic principle number So basic principle number 15 states that in skeleton structures, separate non-structural masonry walls by joints. In flexible skeleton structures, it can be beneficial to separate non-structural partition walls from the structure by soft joints. So this is particularly true for in-plane stiff and brittle masonry walls. So this way, damage occurring even for weak earthquakes can be prevented. So the joints run along columns, structural walls, and slabs or beams, and it must be filled by a very flexible soundproof material such as boards of soft rubber. So in this case, styrofoam and cork are considered to be too stiff. So the necessary joint thickness, typically 20 to 40 millimeter, depends on the stiffness of the structure and the deformation sensitivity of the partition walls, as well as the desired protection level. So generally, the partition walls must also be secured against out-of-plane actions, um, or what we call as plate effect. So in here, a vertical joint separates the masonry wall and the reinforced column. But as we can also observe, it is probably much too thin. So this joint right here, between a masonry wall and a reinforced concrete structure wall, was filled with expanded polystyrene boards. But styrofoam is too stiff for earthquake displacements. Soft rubber would be a more suitable material. So basic principle number 16 states that we should avoid short columns. So the shear failure of so-called short columns is a frequent cause of collapse during earthquakes. So it concerns squat columns, or those columns that are relatively thick compared to their height and are often fixed in strong beams and or slabs. So slender columns can be turned into short columns by the addition of parapet infills in frame structures. So columns under horizontal actions in frame structures may be stressed up to their plastic moment capacity. So in the case of short columns with considerable bending capacity, an enormous moment gradient and thus a large shear force results. So this often leads to a shear failure before reaching the plastic moment capacity. So short columns should therefore be avoided. So an alternative is to design and detail the columns in accordance with the rules of the capacity design, whereby the shear capacity must be increased to account for overstrength of the vertical reinforcement. So we have here, these are considered to be short columns. So the diagonal cracks and shear failures in these short columns of a multi-story car park almost caused collapse. So here, masonry columns in the ground floor of a restaurant behaved as short columns. So they were highly damaged by diagonal cracks. So you can say that a structural member suffered from shear failure due to diagonal cracks in its faces, just like this one. So shear failure in the corner short column of the ground floor led to near failure of this commercial building. Alright, so now basic principle number 17 states that we should avoid partially infilled frames. So the infill of a parapet walls into a frame structure without the addition of joints can cause short column phenomena. So shear failure occurs, or in cases of sufficient shear strength, a sway mechanism develops with possibly significant second order effects or what we call as P delta effect. So in this case, inserting parapet walls into frame led to short column phenomena owing to the good confinement of the transverse reinforcement. No actual shear failure occurred, but an equally dangerous sway mechanism developed, just like this one. So to the left of the destroyed column, there used to be a window opening similar to the one on the far left of the picture, just like this one. The already demolished masonry walls under the window opening behaved like a partial infill wall. So it moved to the right, pushed against the column, and sheared it off. So better transverse reinforcement in the column would probably have prevented the shear failure, just like this one. However, the source of the problem lies in the partial infilling of the frame that caused short column phenomena. So just like this one, no? Here, inserting masonry walls and long window openings caused high additional stresses and column failure. Just like this one. So the relatively good behavior of the massive column to the right in the picture contributed to the fact that the building narrowly escaped collapse. So a possibility to avoid or strongly reduce the unfavorable effect of infill parapet walls into frames is the addition of joints between the infill wall and the columns. So the joint was realized correctly since it is filled by a soft and therefore strongly compatible rock wool sheets. However, the width only permits a 1% free lateral drift ratio of the column. In here, this column illustrates unsatisfactory detailing instead of 135-degree hooks compared with um, basic principle number 25. We are still going to discuss that one. So without the unfavorable effect of the infill walls, it would, however, have behaved much better. So basic principle number 18 says that we should design diagonal steel bracing carefully. So for the bracing of buildings, in particular industrial buildings, steel truss systems can be used. It must, however, be carefully thought out and designed. So the common truss bracing with center connections and slender diagonal members may show a very unfavorable behavior under cyclic actions. So the diagonals yield under tension, lengthening more with each cycle, and end up buckling under compression. So under the repeated cyclic movements, the stiffness of the truss becomes very small at the zero deformation point. So this, combined with the dynamic effects, can contribute to the failure of the structure. So such bracing must therefore only be designed for elastic behavior, or if necessary, very low ductility. So it is advisable, moreover, to check compatibility between the deformations of the bracing and those of the other structural and non-structural elements. So this can indicate the need for more stiff bracing or other bracing systems such as walls. So steel truss systems with eccentric connections and compact members behave much better than trusses with center connections and slender members. So the diagonal elements with broad flange cross sections have buckled about their weak axis and eventually got broken. So that would be all. Thank you so much.